and thank you for making it for the first talk of the day, especially after last night. I actually skipped out to try and sleep, and I ended up waking up at 2 o'clock, and I've been up since. So I apologize profusely as I'm exhausted. Thankfully, I have guarana. All right, so this is exploring the Safari just-in-time exploitation, and one of my pet peeves when I go to a talk or read about a talk is when the speaker gives an abstract or a title that says one thing, but then their talk is actually doing something different. And I'm mentioning this because I'm doing exactly that. The title says just-in-time exploitation, but as I was developing the slides, it occurred to me that the exploitation part of JIT engines is not that interesting because most of the vulnerabilities lend themselves towards full read-write access of memory space. And so for me, the more interesting part is the architecture and the vulnerabilities themselves. And so that's what I'm going to try and focus on a little bit more. So just to give a agenda as to what we're going to cover today, I'm going to give an overview as to why I'm giving this presentation and what I'm going to be covering. I'm going to cover JavaScript core architecture. And for those who don't know, JavaScript core is the name of the engine. It's basically a sub-project for WebKit. And WebKit is the browsing engine that's used by Safari. So if you use an iOS phone, or if you use an iPhone at all, any browser you use on that is going to be based in WebKit. Even if you use Chrome on iOS, that's going to be using WebKit views. If you use MacBook or Mac Pro, that's all going to use, and you use Safari, then that's also going to use WebKit. Then I'm going to go over some vulnerability case studies, and then finally have time for questions. And this image on the right, where it's a URL non-exploit.html, is one of my favorite things about Safari, in that it's very, very exploit friendly. If you are trying to run an exploit and trying to get code execution, one of the things that can kind of get in your way is address space layout. If someone has been browsing a lot, then when they go to visit your malicious page and execute your payload, it may not work and it may crash because of the layout that happened to be just the way things were, just from running things as a usual browser. Safari will see that access violation and retry the entire page, giving you a fresh chance on a fresh address space, which is great for an exploitation standpoint and not good at all from a usability standpoint. So I am Jasiel Spelman. I usually go by Wandering Glitch. Most of this is pretty irrelevant and actually a little bit out of date. The main thing to take away here is if you want to contact me, if you're too afraid to ask questions at the end of this, feel free to reach out and ping me on Twitter or wanderingglitch@gmail.com, or I'm on Freenode and a bunch of other IRC servers as Wandering Glitch. If you have any questions, just feel free to reach out in general. My main task is vulnerability analysis. I'm part of Trend Micro's zero-day initiative team. If you've ever heard of the Pwn2Own hacking competition, that's one of the things I run. I help organize it. We have another one coming up in 2 weeks. Two of the vulnerabilities that I'll be talking about were presented during a couple of Pwn2Owns, and that's about it. Also, this is my second time in Brazil. I was last here when I was 13 years old, and I started loving Guaraná Antarctica back then, and I'm very glad to be back here so I can drink a lot of it here. It's also helping me stay awake, which is definitely a plus. So, an overview. One of the questions I got when I was talking about this in my local hometown where we have a security meetup was, why am I giving this presentation? And there's a quote that one of my coworkers gave. Simon Zuckerbrand also goes by Hex Kitchen. He used to sell vulnerabilities to the ZDI team, and all of his vulnerabilities were use after freeze in Internet Explorer. And we kind of had this internal debate with really all of our researchers, but especially with him, as to how he was finding his vulnerabilities. Because everything he was submitting to us was a very, very clean proof of concept, and you could tell that everything in the proof of concept was there because he knew it had to be there. And then his write-ups clearly showed a great understanding of the vulnerability in all the components. So when we hired him, we finally got confirmation that that was the case, and we requested that he give a presentation as to what his methodology was for finding use after freeze. And one of the things he said during that presentation kind of stuck with me, and that's browsers break perfectly normal C++. And he showed a snippet of C++, not this snippet, but it was effectively the same, where we have a this pointer that we're dereferencing, we're accessing some member object, and then we're dereferencing that, and we're calling some function. This is a pattern that you will see all over the place in all sorts of C++ code bases. However, if the C++ code base is also something that runs JavaScript, this can be incredibly dangerous, specifically because if this func virtual function can call any sort of JavaScript and any user-supplied code, then we may end up freeing the mObject pointer, or we may free our this pointer out from under us, such that subsequent operations are now acting on freed memory, and we'll have a use after free. In a very, very similar way, objects break perfectly normal JavaScript, and objects are the bane of JIT. Anyone that saw Natalie's talk yesterday would have seen at least a little bit of this while she was talking about WebAssembly, specifically because of re-entrancy bugs. So here we have the snippet of kind of worthless looking, but innocuous for the most part looking JavaScript. And this is a proof of concept that 360 Chihu used during one of the Ponda owns, I think a year and a half ago. So we have this function go, and it's doing some writes of some double values into this a variable, a parameter. It's reading one of those values and then writing it to this b parameter, and then it's writing this 2.3 whatever floating point value. And then in the middle, we have this math.clz32 function call. Turns out that because of the way Safari works, because of the way JavaScript core works, if this function gets JITted, math.clz32 will end up being a special function call called an intrinsic, and I'll go over all of this later. I just want to cover it a little bit here. And what will happen is it'll do type coercion on the C parameter if it's not already an integer or a floating point value. When that happens, you're able to break assumptions that have been made such that when you read out from A and when you write out to array 2, you end up being able to trigger type confusion, and you can get an info leak as well as a... and so if we call math.clz32 with an object rather than a integer or a floating point value, any object that has a custom toString or a value of function, then we'll end up being able to break assumptions and specifically be able to trigger type confusion. There's one particular aspect about JavaScript core that makes a lot of these vulnerabilities very, very easy to exploit, and I'll cover that in a little bit. But basically, innocuous looking JavaScript can be very, very vulnerable and can be triggering all sorts of interesting things because of the way that the JIT engine works. So now I'm going to cover a little bit of the JavaScript core architecture, and I'm going to be glossing over a whole lot of it because there's a lot of it that we just don't care about. Main things I'm going to cover are going to be the things that are specific to understanding the vulnerabilities and triggering the vulnerabilities. So in JavaScript core, there's a notion of a JS value, which is a overloaded value, and these are all tagged NaN boxed values. What that means is they're not a number values, and they're tagged such that you have some type information that's put into basically the pointer. So if the upper 2 bytes are all 0, then the rest of the value can be treated as a pointer. Basically, it'll do a quick test to see if the upper 2 bytes are 0, and if not, or if so, then it'll dereference it as if it's a normal pointer and continue on its merry way. If we then look at the signed integer form, if the upper 2 bytes are FFFF and the next 2 bytes are 0000, then the lower half of the value can be treated as a 32-bit signed integer. And then if the upper 2 bytes are anywhere from 0001 to FFFE, then the entire thing can be treated as a double. Doubles are kind of special in the way that they have to be handled, and that's specifically because this very large value has to be added to it. The reason that value has to be added to it is because there are double values that can look like pointers, and that fact alone is what makes a lot of these bugs very exploitable. I'll give an example of just why that can be very bad in a few slides. But if we have a pointer to ABCD, 1, 2, 3, 4, 5, 6, 7, 8, then the upper 2 bytes will be null, and the rest will be that pointer value. If we have a signed integer that we want to represent, and in this case we want 1, then the upper half will be the FFFF0000, and then the lower half will be whatever the signed integer is. And then if we have a double value, it's going to be whatever the double value is with 1 added. So 1.5 is actually represented by 3ff8 and then a bunch of nulls, but because it's a double, because this is a tagged form, it's actually being represented as 3ff9. The next very important thing to understand are arrays, and there are 5 or 6 different types of arrays in JavaScript core. I'm going to talk about 3 of them. Specifically, 2 of them are very, very important, and not actually this one, but it's useful to know this one anyway. This one is an array with int32, which, as the name kind of says, is an array with signed integers, signed 32-bit integers. So we create it with new array 1, 2, and then the upper half of every value in this array is going to be completely worthless because all of it's going to be FFFF 0000, but then the lower half will be that signed integer value, signed 32-bit integer value. Now we have array with double. This is basically the most important format because all of the values here are stored in their native double form. So 1.5 and then 2.5 are the 2 values that we're placing in this array with double, and they're being represented by 3ff8 and 4004. Whereas in the previous slide, I did mention that 3ff9 is the tagged format, 3ff8 is the native format and how it gets stored. The last array type I'm going to talk about is an array with contiguous. Despite its name, all 3 array types here are all contiguously allocated. It's just named that because I don't actually know why. It's kind of an overloaded term, and what it means is that this will have JavaScript types, or sorry, object types of all, it'll have JavaScript variables of all types. So objects, integers, and doubles. And there are also transitions from one array type to another. So if we have this array with int32 and we write an object to it, then that first value is going to stay the same, but now this array is going to be considered an array with contiguous. If we do the same thing with the array with double, where we perform a write to the first index, we'll also convert from an array with double into an array with contiguous, but note that the 3ff8 is now becoming a 3ff9. And just to drive that very, very much into everyone's mind, here we have an array with 5.67 blah and then 2.5. And then if we look at it, that's 68, 63, 74, so on and so forth. That could be interpreted as a pointer because the upper 2 values upper 2 bytes are completely null. But this is an array with double, and so the engine itself knows not to do that. If we then perform that write, where we're now converting it from an array with double to an array with contiguous, it adds 1 specifically so it knows never to dereference that because that is not something that should be safely dereferenced. Now I'm going to give kind of an execution timeline. This is how JavaScript goes from being executed or being seen by the browser and then executed by the engine itself. It goes through a parser, which has a parser and an elixir. It goes from there, it gets converted into an abstract syntax tree, which then goes to the byte compiler. The byte compiler will then emit bytecodes that will go into the low-level interpreter. The low-level interpreter is the first piece to actually execute any of the JavaScript that it sees. It then goes into what's called the JIT, which is the baseline JIT. Despite the name, it doesn't actually do any real performance speed up here. It's just the name they chose. After that is the fastest sublight engine. It's called the data flow graph, where a lot of optimizations actually happen and a lot of vulnerabilities exist. And then finally, there's the FTL, which stands for faster than light. And just going a little bit more deep into each of those. We start off with the parser, which has a lexer and a parser. The lexer just converts scripts into tokens, and the parser will convert the tokens into the syntax tree. And this is also where any sort of grammar enforcement occurs. So you can't just have some JavaScript that says like throw, try, catch, finally. It'll catch it right here, and it'll break it out here. One thing is I've not seen any real security vulnerabilities here. I don't necessarily know that that's actually accurate, however, because WebKit does obfuscate commits. Of my vulnerabilities that I've submitted to WebKit, if you were just looking at the commit tree, you would not actually know for sure that they're vulnerabilities because there's no information there to actually tell you. It just makes it look like they're fixing some random bug that they came across. So it's possible that I missed something in one of the commits I was going through. All right, the byte compiler, as I was saying, is going to consume the abstract syntax tree and then produce internal bytecode. There's not much to it that's interesting from a security point of view. However, there have been vulnerabilities here. That said, they've chosen not to patch it here, but instead choose it where the bytecode's being acted upon rather than where it's being created. I don't know why they've chosen that, but that's just what they've done. And then finally, we're down to the low-level interpreter where execution of JavaScript is actually happening. They're not caring at all about executing anything quickly because their entire goal here is to start execution as soon as possible. So basically, start up the engine with very, very lightweight code and then start running as whatever bytecode they can as they can. It won't run very performant at all, but they will collect some data so that they can then run other layers faster. And yes. One crucial thing about this and the other layers is that they all share a calling convention because you can be in one function that is being executed at all 4 engines basically at the same time or at different levels in the stack. The way they do this is something called the OSR entry and exit, which stands for on-stack replacement. And they all share a calling convention to allow for this. Tier up is going to happen based on metrics, and those metrics are going to be function hit count and then loop hit count. So if you have a function that gets called over and over again, that's going to affect it. If you have a loop within that function that's being called, then that's going to affect it even further. And again, because the low-level interpreter is designed specifically to execute bytecode rather than to execute it quickly rather than fast, it also performs JIT all in another thread so that this is all done without the user noticing. Once we tier up from the low-level interpreter, we'll hit the baseline JIT. And the baseline JIT is only going to optimize function calls. So if you have any sort of JavaScript that does a lot of math or does like string manipulations, you're not going to get any benefit whatsoever from this tier. However, if you call JavaScript that is making a lot of function calls, especially function calls that end up calling native code, you'll get a huge benefit from here. Additionally, like the low-level interpreter, this will collect data to feed to the faster engines. Now we're on to the data flow graph, and this is the fastest sublight engine. This is the most interesting engine, at least to me, out of all of them, where it'll apply classic compiler optimizations, and I'll show an example of this in a little bit. It'll optimize certain function calls. I kind of touched upon this when I was talking about math.clz32 in that beginning slide. And then it'll also do things like bounds checking removal and array type check removal, which may seem dangerous at first because it is, but there are safe ways of doing it and there are reasons to do it while actually caring about performance and security. So here's just a very basic snippet of JavaScript. We have a function bar, it takes a parameter x, and then we have a for loop that's going to iterate 10 times and basically initialize an array with I plus 3 times 456 times x. When the JIT sees this, it'll see the 3 times 456 times x and then immediately convert that over to 1368 times x, and then it'll see that, hey, we don't actually use the 1368 times x doesn't depend on anything inside the loop, so we can hoist it outside the loop and continue executing. Although this is a very basic example, the main reason to show this is the DFG is going to, or is capable and allowed to move code around, which can be very, very dangerous. It can also be very, very performant. Just trying to make it very, very clear and aware that there are cases where it's going to do some interesting things to your JavaScript. This is an example of one of the function calls that it optimizes. This is math.clz32. In the top part of the image, we have, probably not very readable, it's okay. That's from the runtime where it's basically defining the function and defining how it goes. And it's just saying that, hey, this function has an intrinsic. It has a version that is going to be far more optimized and far faster to run. At the bottom, we have a snippet of code from the DFG's bytecode parser, where it's going through and seeing, hey, we have a CLZ32 intrinsic being executed or being used in this function. In this particular case, it has an explicit check to see if math.clz32 is being called with no argument. at which point it's going to replace the call with a constant value of 32. Otherwise, it's going to add a bytecode for arith CLZ32 and use whatever argument was specified. And then here, I'm going to just talk about the array type check removal and the bounds checking removal. So on the left side, we have function bar, and we have 6 writes that we're performing to it. If we go through normal JavaScript, we're going to hit array 0 and set it to 1.1, and it's going to check, is the array actually larger than 1? When we hit array index 1 and write 2.2, it's going to check, hey, is it greater than 2, so on and so forth. We're going to end up with 6 array length checks for these writes. When it goes through the DFG JIT, it's going to see we have 6 writes, and it's going to do 1 check and just do 1 comparison, because after that, it can bail out and throw an exception or whatever based on those values. But it only has to grab the length and do that comparison once, as opposed to doing it for each operation. On the right side, we have bar, this time taking an argument, and we're doing basically the same thing. But here, it's going to see that, hey, we're writing doubles. We can do 1 check of the array at the beginning of the function, see if we're operating on an array with double. That way we know whether or not we have to write 1.1 as a tagged pointer by adding that 1000 value, or if we can use the native format. Additionally, we don't know what x is, but we can do a type check on it, and then afterwards, when we're writing to array index 4, the 5.5 value, we can either then write a tagged value or a non-tagged value, depending on whether or not that write from x coerced it into an array with contiguous or not. And this is just some of the stuff that DFG has to keep track of. And the way it does at least some of this is with the 2 different giant switch statements. One is in DFG clobberize, and then one is in DFG abstract interpreter. DFG clobberize will attempt to safely model, actually both attempt to safely model all the operations of any bytecode that it tries to execute. The worst cases are shown here, where you have some switch case statements, and then you end up in a call to read world and write heap, or you end up in a call to clobber world. The read world, write heap basically says, we have no idea what this operation can do. Assume it will destroy everything that we possibly have a reference to. Assume it will read everything we may have a reference to. And the whole thing here is basically no lengths are to be trusted after this. So if we grabbed an array length before this, we need to re-grab it again. If we have access to some object's property bag or a structure, we need to re-grab it because all of it may be invalidated. The clobber world basically says, hey, we previously thought that this function or this array was an array with double, it was an array with contiguous. We need to recheck all of that afterwards because it may have changed around us. I have no idea why they chose to have this handled in a number of switch statements, because there's another one for whether or not an operation can initiate garbage collection. There's several others similar to this, and there would have been cleaner ways to do it, specifically because some of the vulnerabilities that have arisen because of mismatches between the DFG clobberize and the DFG abstract interpreter, where basically one was properly modeling the effect of something, whereas the other wasn't. They recently, as of May, maybe March, started trying to track this, but they started tracking it using dynamic instrumentation and only for debug builds that they themselves are running. So unless one of their tests catches it, there's going to be a lot that they're going to miss. All right, the last backend is the last engine is the faster than light engine. It currently uses a special backend known as B3, or the bare bones backend. It used to use LLVM, but what they found is that LLVM is much better at optimizing entire functions rather than single functions at a time. So they wrote B3 specifically to optimize small functions at a time. WebAssembly will compile straight to B3, and there have only been a couple of vulnerabilities here, but one thing to note is that all integers at this level are signed, and they'll be very, very important in a second. I don't know why they made that decision, but it's strange, and that's just what they went with. So the first vulnerability I'm going to talk about is CVE 2017-2547. This is a vulnerability that was found by Tencent and then used in Pwn to Own. It was also found by Loki Hart of Project Zero, just general bug collision. I think he found it it was after the contest anyway. And whenever I see a proof of concept, even if I already have details, I try to ignore whatever the researcher has given me, and I try to go from the crash and from the proof of concept just because it makes it better for me to understand what's going on, and it's just easier for me in general. And so if we look at this, we have a crash, and one thing that should be noted is that we have a crash at 41, 41, 41, 41, so a bunch of A's. If we look at the proof of concept, the one thing that stands out is that there are no A's anywhere in here. But we can continue on. And if we look at it, we have this bar function being called 5,000 times. And then inside the bar function, we have this loop that's going to iterate 20,000 times. And we have a subtraction that's being done, but it seems rather pointless because the value is not actually saved. The whole reason for this is to trigger the DFG tear up and to trigger a FTL tear up. At the end of the bar function, we have array being accessed at a negative index, so -3, and then being added to array 2. And if we look at these values, this is 3.54, whatever, that ends up being 41, 41, 41, 41, which is the value we were crashing at. So looking a little bit more at what's going on, I'd mentioned that the DFG engine performs array bounds checking removal. That happens in a phase called the integer check combining phase. What happens is it'll see that there's some array bounds that are being accessed, and it'll try and build up a list of minimum nodes and maximum nodes. And then if necessary, it'll go ahead and delete nodes where they're redundant or they're kind of superseded by another index. So looking at it a little bit more closely, if we have constant values, so we don't have a variable that's being used as an index. In this case, we have the -3, we have the 2. Then we'll set the minimum node to 0, and we'll set the maximum node to whatever is that integer constant. And then at the end, we'll add a check-in bounds, which is a special bytecode operation that just says, hey, just check if this value is actually in bounds based on the array size or the object size, whatever we're operating on. And if we look at the FTL code that's used to handle this, it actually looks okay. We see compile check-in bounds. It has speculate, so it's speculate out of bounds if the length is above or equal to the size of the array. And for those who spend a lot of time doing any sort of assembly, above or equal, you know, is the unsigned way of handling anything. But if you were paying attention during the overview where I was talking about the FTL, you'll remember that the FTL only deals with signed integers. The above or equal operation actually gets converted into a greater than or equal to operation. And so if we look at our proof of concept again, we have array -3. -3 is never going to be greater than whatever the array size is, so it'll continue on and it'll just go on and execute. Basically, this vulnerability allows for an out-of-bounds read leading to type confusion. It's also great because it leads for both leaking objects as well as crafting pointers. Because here, the crash we examined, that was controlling a pointer and getting it to dereference as our choosing. If we wanted to, we could create another array, say array 0, and have it allocated before array 1, and then run the same bar function, but instead have it access array 1 and do an out-of-bounds read on that, because then it would read the pointers from array 0 and return them back as floating point values that we can then convert into something that we can actually use. And so this was a very, very good bug, and this is a great example as to why the exploitation piece of JIT vulnerabilities is not that interesting to me, because when you can do something like that, you can very easily and very quickly get full read and write access to all of memory, at which point it's game over. There's really nothing you can do, but the vulnerabilities themselves are still very, very interesting and quite fascinating to me. So the next vulnerability I'm going to cover is CVE 2018-4162, and this is one of the ones that I found. It was not the first one I found, but it's one of the more interesting ones, specifically because of the way I found it. I was surfing Reddit at home one day and was linked to a Stack Overflow post where someone was asking basically this question. So they went to a job interview and they were asked, with this JavaScript snippet, can A equals equals 1 and A equals equals 2 and A equals equals 3 ever be true? They weren't sure, but the answer is yes, because JavaScript. Specifically, if A is an object and has a custom value of function or a custom toString function, you can have an internal iterator and basically choose a new value every time you get compared. And so just kind of get an example of that, you have two different ways of testing for equality in JavaScript. You have like 1 equals equals true, 1 equals equals 1 inside a string, and both of those are true. This is loose equality, or loose comparisons. And then we have 1 equals 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 true, basically 3 equals instead of 2, and you have here you'll do a type check before you actually do the value check. Whereas loose comparison will do a check by doing type coercion first. This will try and make sure, strict comparison will make sure that the objects are the same type before continuing on. And just as a quick example of what that might look like, here we have 1 equals equals, and then I have this custom object that has a custom value of function that when executed is going to print out we got called, and then it's going to return the value 4. And if we look right after, it gets we got called gets printed out, and then false is printed because 1 is obviously not equal to 4. When I was looking at this, I decided not to look at the DFG clobberize or DFG abstract interpreter. I just had a feeling they had not actually properly handled this, and so I just created a proof of concept and immediately got a crash, confirming that I was right. So here we'll go over the entirety of the proof of concept. Starts off with creating an array, and I didn't cover the, or I forgot to add a highlight for the next line where I'm setting array1.a to 1. The whole reason for this is to invalidate the structure for an array, and that's going back into JSC internals that I was kind of glossing over. Main thing is that that's just a prereq in order to hit this particular bug or hit a couple of other similar bugs. I'm now calling this go function a very, very large number of times. The whole reason for this is specifically to make sure it hits the DFG. With this particular proof of concept, we'll hit the FTL, but it's not that big a deal. We're not going to notice. This runs in about a second, if even that. We're going to perform a couple of writes, basically just trying to get the JIT to understand that we're writing double values into this array and that this is an array with double, and just kind of reinforcing doubles all the way down. At the end, we're performing this write again, this 5.67 whatever value, and this ends up just being 0x glitch, just to prove that we have a pointer that's under our control. And then in the middle, right before that write, we have C equals equals 1 to actually trigger the vulnerability. Then the last time we call it is calling go, this time with our custom object. We're using toString instead of value of here. It doesn't matter, both would work. Within the toString function, we are setting the 0th element in array1 to a object. So this is going to convert the array with double into an array with contiguous. The problem is when the go function within the JIT goes to run that, goes to perform the write of 5.67, so on and so forth, it still thinks that this is an array with double. It hasn't invalidated any of its assumptions, and so it's going to perform that write without tagging it, which means we're able to control what pointers we write into this array, and later when we do a string concatenation with it, it ends up trying to dereference that pointer. That pointer is not valid because I'm just showing a proof of concept. And so we get a crash and nothing too bad happens. But with any sort of control, we are able to get full code execution just based off this. If we look at the the DFG abstract interpreter and the DFG clobberize, we'll see that they actually do have case statements for these opcodes, but nothing all that interesting actually happens within it. Basically, all they're trying to do is see if there's any opportunity to optimize this function call to try and make it much faster. So are they looking at, are both arguments constant integers? Are they constant doubles, whatever? And if so, try and do the comparison there to try and replace the call altogether. Otherwise, we'll have to continue on and actually execute it every time the function gets executed. I also wanted to demonstrate just how easy this is to turn into an info leak. All we have to do is create a float64 typed array. This is a typed array that basically just all the data that it stores is going to be doubles. We have a couple of helper functions. All this is going to do is create two typed arrays, a uint32 typed array and a float64 typed array, both of which have the same backing array buffer. The reason for this is we're going to write a float64 array value to it. We'll write a floating point value to the float64 array, and then we'll read out two 32-bit values from the uint32 array, and then just basically add them together. Here I'm doing string math, but if we're actually doing anything, we'll have to shift the value so that it forms an actual pointer and go on from there. And then all I've done is, instead of performing that write at the end of the go function, here we're performing a read from A0 and writing it to our float64 array from all the way at the top. And then at the end, I'm performing conversion on it and then just printing out the value, allowing for a very quick and easy info leak. So one of the things I really, really like about JIT vulnerabilities is that they very much lend themselves to exploit reuse. And what I mean by that is writing an exploit takes a lot of time. With JIT vulnerabilities, especially JIT vulnerabilities of this type, there's a lot of them where all you have to do is swap out one function, one call, one whatever. So in this case, we have the proof of concept on the left. C == 1 can be replaced by ... C, which is the spread operator. It can be replaced with math.clz32, can be replaced with math.abs, can be replaced with that, or it can be replaced with any of these. I guess could is the better way of saying that. These are all patched now, but at one point you could have written one exploit and then used any of these to actually trigger any of them. And I just really enjoy that because it makes it very, very nice from an exploitation standpoint. As someone that uses any of this software, it's terrifying because, again, exploitation takes a lot of time, and this massively shrinks the amount of time that you have to invest in doing any of that. An interesting thing to note here is that there have been a couple of vulnerabilities here that apply to both Chakra core, the JavaScript engine for Edge, as well as the engine here, JavaScript core. The spread operator one, the ... C, and then also the == 1 applied to both, both of which are now patched, but it's interesting. And on that note, I am pretty much done. One thing that, kind of expanding on what I just said about the two that affect both Chakra and JavaScript core, it's interesting in that they both have different devs, entirely different dev teams, but they're both building off of the spec. And it's interesting to see how some of the vulnerabilities kind of exist across all the browsers because they're all doing things very similar ways, and the spec doesn't specify one thing or the other, and they're just trying to be as performant, but also trying to support as much as possible. And that's just kind of nice. And on that note, does anyone have any questions?